Hello and welcome. My name is Travis Krebs. This is a presentation for my PhD final examination for my dissertation, which is titled A Distributed Doublet-Based Method for Unsteady Aerodynamic Analysis with Relaxed Wakes. I'll start with a brief overview of the presentation. So I'll begin by covering some introductory material, including the motivation behind the research and some background on potential flow methods and unsteady analysis. I'll then move on to discussing my research, including the method and a couple of the studies I performed with it. And lastly, I'll close out with some concluding remarks. So, computational methods form an important part of the aircraft design process. They allow us to quantify the performance of a design without necessarily requiring experimental testing. Broadly speaking, most prediction methods fall into one of two categories. We have quote-unquote high-fidelity CFD methods, which discretize the flow field and solve the Navier-Stokes equations across the resulting cells in the control volume. Then there are quote-unquote low-fidelity potential flow methods, which often use surface-based singularity representation, and their low cost stems from simplifications to the governing equations. So typically they model the flow field as irrotational, inviscid, and incompressible. Now, with that in mind, new and unconventional aircraft configurations are growing increasingly popular. For example, here we have the NASA X-57 Maxwell, which has 12 inboard propellers and 2 wingtip-mounted cruise propellers, so definitely an unconventional aircraft. Another example is given by multi-rotor drones, which are incredibly popular. But from an aerodynamics perspective, these sort of aircraft pose a problem. They often operate under unsteady conditions. So whenever we have rotors or propellers operating in close proximity to one another or to other aerodynamic surfaces such as wings, the resulting flow field is transient. So there's some time dependence there. And due to reasons which I'll touch on over the next few minutes, these aircraft are challenging or infeasible to model with existing potential flow methods. And what that means is there aren't any computationally inexpensive methods out there that can reliably model these systems with adequate detail. This leaves CFD as the primary investigative tool, which is less than ideal due to the high computational expense. It's hard to look at a range of designs to identify trends, for example, when the computational cost is so high. As a result of this, the purpose of this research is to develop a low-cost, robust method for unsteady aerodynamic analysis so that we can analyze these new and complex aircraft configurations at a lower expense. So, as I mentioned, unsteady analyses have a time dependence, and that can be cyclical. So, for example, the advancing and retreating blade effects acting on a rotor in forward flight, or propeller-wing interactions. Or these effects can be non-cyclical. One example being a wing flying through a gust, or the effects can be a combination of the two, like a rotor undergoing a flight maneuver, which has both advancing and retreating blade effects, as well as the effects due to the flight maneuver itself. So there are certain necessities for unsteady analysis, and I'll be speaking now from a potential flow perspective specifically. The first requirement is modeling the shed circulation. And what I mean by that is the strength of the wake in the streamwise direction. So for example, here we have a 2D airfoil which has some transient free stream velocity u. The strength of the wake given by gamma w also has a time dependence because the strength of the wake is determined by what's happening at the surface at the moment that it's shed. So modeling the wake strength and how it changes in the streamwise direction is one important aspect of unsteady analysis. Another requirement is the approximation of apparent mass, which is a non-circulatory term that acts as an inertial force opposing the acceleration of the airfoil due to the surrounding air mass. So unsteady aerodynamic systems have a time dependence and require specialized analysis. The modeling of the shed circulation and apparent mass are important, but they also happen to be the reason for some of the instabilities inherent to unsteady potential flow methods. To explain that point, I'll have to give a general overview of Vortex filament-based potential flow methods, which will provide context. So these filaments are the building blocks of many potential flow methods. In theory, they are infinitely thin, and the velocity they induce approaches infinity as you approach the filament. In actuality, this is often corrected using solid core models, which correct the velocity within a radius of the filament. These filaments are often used to build vortex rings, which are closed loops with constant circulation strength. And these rings, in turn, are often used to model wings and wakes within a vortex lattice method. So for example, here we have a wing half-span modeled using lifting surface method, which places the rings on the camber line. The wake is also made of vortex rings. This is a very typical representation of what is known as a unsteady vortex lattice method, or UVLM. And most of the time with conventional wings and wakes, this is fine. UVLM-based methods have incredible value and are computationally inexpensive. The issue is when we get near to the surfaces or the wakes, large induced velocities can still be found because of the filaments. The closer we get to the surface, the more apparent the problem becomes. So if we were to model a system with complex interactions between surfaces and wakes, like a propeller wing system, for example, where the wake of the propeller passes over a wing, we can run into trouble. Any system with a lot of vortex rings acting in close proximity to one another is susceptible to problems. In addition to this, filament-based methods like the UVLM have wake element sizing constraints for their stability, which are due to the apparent mass approximation, which uses a finite differencing method. So in addition to any issues the filaments might cause, we have stability constraints on the analysis, which are not always easy to fulfill, particularly when analyzing rotors or propellers. So as a result, analysis of complex interactions using vortex filament-based methods can be problematic. These methods are not ideal for the sort of complex surface wake interactions that we need to model in order to predict the performance of, say, a quadcopter. We need something a little more robust. So the problems I just mentioned are directly related to vortex filaments. One of the ways we can address these problems is by using distributed elements, such as vortex or doublet sheets. These elements effectively distribute the circulation contained within a filament across a surface. As a result, the velocities induced by these sheets under certain conditions are bounded everywhere. That means that it's possible for these sheets to produce no infinite or near infinite induced velocities. An example of this is given by the DVE method, which models steady wakes with only vortex sheets. So the wake relaxation is very robust. This image here is an illustration of that. However, the DVE method still uses filaments on the surface and within unsteady wakes. But what about removing all filaments and moving to a completely distributed based method? One example of this is Pan-Air, which uses distributed doublets and source sheets with no filaments whatsoever. Pan-Air can be used as a panel method or a lifting surface method, but Pan-Air can only do quasi-steady analysis. So a fully distributed based method for unsteady analysis is needed, something with the capability of modeling the X57 Maxwell or a quad rotor, for example, within a fully unsteady framework and with a relaxed wake. And this is where my research comes in. The distributed doublet element or DDE method solves these problems by using only distributed doublet sheets to model everything. DDEs are planar triangular elements, and they have parabolic circulation distributions in both the spanwise and streamwise directions. And just to be clear, the DDE method assumes the flow is inviscid and incompressible. We aren't using any viscous corrections or approximations. The DDE method uses a lifting surface representation, modeling surfaces as infinitely thin by placing the elements on the camber line. So here, for example, we have a wing half span with a four-bladed wingtip mounted propeller modeled with DDEs. This method uses continuous strength distribution, which means the doublet strength across the entire surface and wake is continuous and uninterrupted. This results in a velocity field that is bounded everywhere. There is no near infinite induced velocities because the system is fully distributed and the strength is continuous and uninterrupted. As an illustration of this, here is a planar elliptical wing with the circulation strength distribution overlaid on top. At the leading edge and wingtips, the strength is 0. Across elements, it's continuous, and at the trailing edge, that strength is carried into the wake, which isn't pictured here. The real key takeaway from all of this is now we can model streamwise changes in wake strength without needing vortex filaments. This means we can model robust, unsteady, relaxed wakes without issue, which is a huge advantage. The DDE method uses a time-stepping procedure, and the wake relaxation takes place alongside that. So here, for example, is a graphic of a quad rotor ascending in flight. The blades are shedding wake elements as they move, and these elements are relaxed as that happens. And even though this analysis has a lot of wake interactions, there are no issues, no large non-physical velocities or anything like that. With the DDE method, the forces are calculated every time step, and that's done using the Cont'd theorem, not a pressure integration scheme. And because we're using the Cont'd theorem, the DDE method doesn't need the sort of geometric fidelity necessary for pressure integration methods, which need the leading edge modeled at a certain resolution in order to capture the forces produced there. Apparent mass is approximated after the time-stepping procedure using a finite differencing method, and this is because the apparent mass approximation depends on the time rate of change of circulation. So all of this put together means that the DDE method is a robust lifting surface method capable of fully unsteady aerodynamic analysis. Due to how the method was developed, it avoids a lot of the numerical issues present in conventional methods. And with that, we can now get into some of the results that the DDE method has produced. So unfortunately, due to time constraints, I can't touch on many of the validation studies performed with the DDE method, but they are provided in Chapter 4 of my dissertation. Here, I'll cover the results of the final validation study, which looked at the transient thrust loads predicted by the DDE method. Transient blade sectional thrust coefficients were compared to a CFD analysis of a small 12-inch rotor at these operating conditions, which represent the general operating conditions of a rotor in forward flight. The data that we're comparing to here is one of the only published data sets that contains transient rotor loads, so this is still an emerging field. Not a whole lot has been done in this area as of yet, so this is significant. And here we have the comparison of the blade sectional thrust coefficients with the CFD results on the left and the DDE results on the right. It's important to remember that the DDE method assumes the flow is inviscid, so we aren't exactly comparing apples to apples here. The azimuth location represented by psi is 0 when the blade is pointed downstream. 180 degrees means the blade is pointed upstream, so 90 and 270 degrees are where the blade is advancing and retreating respectively. And right away we can see that the analyses agree in magnitude and radial location across most of the rotor disc. For example, this area of peak sectional thrust at 100 to 110 degrees is common in both, as well as the tapering off of the thrust as the blade passes 180 degrees, and the near zero thrust on the retreating side. There is some discrepancy at 0 degrees where the thrust is about to begin recovery. At this point, the blade is producing very low amounts of thrust and is also engulfed in the wake of the rotor, so it represents a very chaotic region. In terms of computational expense, we know that the CFD prediction used 512 8-core processors and needed 256 gigabytes of RAM for the grid generation. We aren't sure of the wall clock time on this analysis. It wasn't provided. In contrast, the DDE method used a single core and 16 gigabytes of RAM with a clock time of approximately 25 minutes. So this is a good example of how the DDE method can offer a reasonable prediction within a comparatively short amount of time. This is the strength and the purpose of the method. So in summary, the DDE method is capable of predicting the transient thrust of a rotor operating under unsteady conditions. And with that, let's move on to a sample application of the DDE method. So the purpose of this study is to quantify the effects of advancing and retreating blades on the thrust of a rotor. The DDE method lets us do that because the computational cost is low, so we can run a bunch of analyses and then look at the larger trends in the data. So 2 rotors, including the APC rotor introduced on the previous slide, were evaluated at a number of different normalized free stream velocities and 2 tip path plane angles, 0 and 15 degrees. So for example, here we have data for the APC rotor in fully edgewise flight for a number of different forward speeds. The azimuth location on the x-axis is the same as before. 0 and 180 degrees correspond to the blades pointing up and downstream. We have this symmetry to the plot due to the prop being 2-bladed. So all of the effects are 2 per revolution. What we see in this data is large variations in the thrust coefficient over a single rotation. At a high advance ratio, like this dashed red line with the circular markers, the thrust bounces around between 0.013 and 0.022, and this happens twice per revolution. So these are quite large oscillations, and in order to get a bigger picture, let's look at the oscillation amplitudes. For each data set, we looked at the maximum and minimum thrust and normalized the difference between the two with 2 times the mean thrust. What this gives us is the amplitude of the oscillation in the thrust coefficient. Here we have this normalized thrust oscillation amplitude plotted against normalized free stream velocity for all of the data. So at a normalized free stream velocity of 0, at the origin the rotor is in hover, so we would expect 0 oscillations in the rotor thrust because there's no unsteadiness there. Then as we increase forward speed, the oscillation in the thrust grows as the transient effects become more severe. At higher forward speeds, the amplitudes are quite large. Looking at the T-motor results here on the black line for a tip path plane angle of 0 degrees, this data point in the far upper right corner of the graph corresponds to the rotor at 3000 RPM at about 25 meters per second forward speed. And here the T-motor has a normalized thrust oscillation amplitude of over 0.3. Another way of saying that is the rotor thrust oscillates by over 60% of the mean, and this happens twice every revolution. So the thrust of a rigid rotor in forward flight can be highly transient. The amplitude of the oscillation can be in the same order of magnitude as the time average thrust coefficient itself, which is interesting. And this sort of analysis, particularly the edgewise flight analysis, wouldn't really be possible with existing potential flow methods. And this is the primary benefit of the DDE method. It gives us the ability to take a big picture look at trends across a range of operating conditions so that we can understand what's happening. So in conclusion, the DDE method is a new approach to unsteady analysis. Due to the way that it was developed, the velocity field it produces is bounded everywhere, and it's free of the constraints imposed on conventional methods. This allows us to use it to look at complex aerodynamic systems like multi-rotor drones, for example. The method was put through a series of validation studies which showed that it's capable of predicting transient rotor loads ultimately. And then the method was applied to the sorts of analyses that would be infeasible otherwise. Ultimately, the method could be teamed with an optimization process to develop new designs, which is one of the main benefits of lower fidelity potential flow methods in general. So this concludes my presentation. Thanks for watching, and I hope it was informative. I'll close out with this slide, which contains the information for the images I used within this presentation. Thank you very much.